Hello, good evening, good day, and welcome to the latest episode of the Ask Abhijit show. I hope you're all doing very well. Today, we discuss science, which is everyone's favorite subject, as we know. So, let's see who all is there with us today. I can see Praful, Crazy Brain, Durga, Dr. Nishchay, Alpha, Rishikesh, Nikhil, Vineet, Prabal, John Tiru, GK, TK, Priyanshi, Neelansh, Dungar Singh Chauhan, Vidyarthi, Lakshya, Ayush, Tiwari, Sangeet Lover, Ambarish, Rahul, Chiching, Dharmendra, Ram, Ram Samir, Nikhil, Kirito Ito, Trupti, Vladimir Adityanath, Nilansh Goel, Rahul, Dharmendra, Crazy Boom, and lots of other people. Let's see who else is there. Pratik, Nikhil, Ayush, Hideki Ryuga, Shivaji Itape, Mac Per, Anish, Shri Harsha, Lineshwar, descendant of Rigvedic clans, Sahil Verma, Neil, and lots of other people. Shashank, Shurveer, Edith, someone, Kumudini, Manojit, Roger Fighter, Jason, and so on. Good evening, good day, all of you. So, shall we get into the questions? As we always do, without further ado, let's get right into the questions. Samir Joshi says, why don't we feel the Earth's rotation? Why don't we feel it? So the Earth rotates, goes round and round, right? So why don't we feel that? And the rotation speed is reasonably fast. Let's take a look at the screen, shall we? What does the Earth look like? The Earth is a planet. Google Maps. Where is Maps? Here is Maps. So it's reasonably round and it rotates. It rotates from east to west. I believe that's the rotation direction, or whatever it is. I mean, the sun rises in the east, that's what we know, and the Earth's rotation is reasonably fast. I mean, 500 kilometers per hour per second, something like that. Whatever it is, you can look it up. It's a fast rotation. So the question is, why don't we feel it? Why aren't we thrown away when the Earth because of the Earth's rotation? Why are we just here where we are and we feel nothing? Think about it this way. Let's say you're sitting in a car. The car is traveling at, let's say, 50 kilometers an hour on your road. Yes. Do you feel something happening? You feel some movement from time to time, which is when the car accelerates or decelerates or changes direction. But if it is just going straight without changing its speed or velocity, you feel nothing. You can just sit comfortably in there and nothing happens. Let's imagine you're sitting in a plane, in an aircraft. So the aircraft, you get inside, you say, you take your seat and all the formalities are done. Then the aircraft goes towards the runway. Yeah. Then it lines up with the runway, and then the pilot turns on, throttles the engines, and the engines go full blast, and that's when you are pushed back against your chair, right? When the plane accelerates. So once again, it's only when you're pushed back, when the plane accelerates and changes speed, that you feel the movement. But once you're in the air, once everything settles down, you feel nothing. You can walk around and do whatever you want. You can have food. Yes. So the same thing happens on the Earth. When you're sitting on the planet is moving at the same speed. The speed isn't changing. There is no acceleration or deceleration. That's why you feel nothing, right? You're essentially in a quasi inertial frame of reference. That's how it feels like from your perspective. It's not exactly an inertial frame of reference, but yeah. So as long as there is no acceleration or deceleration, you're gonna feel nothing, because you are attached to the planet, your feet, your chair, whatever, your bed, yeah, and you are part of it essentially, and you feel nothing because it's going on at the same speed. The rotation isn't slowing down or speeding up. If for whatever reason the rotation were to suddenly speed up, yeah, that's when you will feel it. That's when you'll be thrown in some direction. Or for some reason, if the rotation were to suddenly slow down, you would again feel the same kind of thing, and you'll be thrown in the opposite direction. But as long as the rotation is the same speed, you feel nothing. Because of how you feel in a car, when the car is going at the same speed in a straight line, you feel nothing. When you're sitting in the plane is flying at the same speed, you feel nothing, right? And when the plane is taking off, or landing, or when there is bad weather, the seat belt sign comes on. So that's what tells you that yeah, right now there's going to be some acceleration or deceleration or movement from side to side, and we need to be in the chair, otherwise we will be thrown out. Yeah, we will face some kind of problem staying where we are. So that's why we need to sit down and put on the seat belt, and that's how it goes. So that, in brief, is why we do not feel the rotation of the Earth. Hmm. Okay, let's take another question. The next one. Swapnil Mishra says, uh, two questions. Firstly, which aspects of photosynthesis are still not well understood by science? And secondly, since solar panels take up so much land space, is it possible to optimize plants directly or indirectly to harness solar energy through artificial photosynthesis by converting sunlight plus carbon dioxide plus water into clean fuel? Okay. So, photosynthesis, which aspects of photosynthesis are not well understood by science? So, first, let's talk about what we do understand about photosynthesis. Photosynthesis is the process, the reaction by which plants convert sunlight and water and carbon dioxide into a different form of energy, which is essentially glucose and carbohydrates, and they give off oxygen as a byproduct, right? So, how does this happen? Plants have leaves, we know them, right? We see leaves everywhere. Yeah, these leaves, they in the cells of these leaves there are organelles. So like in the human body there are organs, within a cell, within the cells in our bodies and in the cells of plants, you have organelles, which are different components that carry out various functions. So one of these organelles inside a cell, inside a plant cell, a leaf cell, is called a chloroplast. Chloroplast. Now, this chloroplast organelle contains a pigment called chlorophyll. Now, what does this chlorophyll do? It's a pigment. It absorbs energy from the light waves, which is the rays of the sun, the photons that come from the sun. Now, if you look at the sun's light, it is white light. It looks yellowish, but it's actually white light. It's a combination of all the different colors of the visible spectrum and much more. So it's white light. So the chlorophyll absorbs not all of this light, but some of this light. It absorbs the light photons in the blue part of the spectrum and the red part of the spectrum, and it reflects photons in the green part of the spectrum, which is why plants and their leaves appear green. Okay, so the chlorophyll absorbs this sunlight, the energy from these light waves, and this energy is converted into chemical energy in the forms of a couple of molecules: ATP, adenosine triphosphate, and something called NADPH, which you can look up. I don't remember the exact full form, but these are two molecules that store energy. Essentially, they are related to the energy, and we also have ATP, etc., in our bodies. So chlorophyll, by some process, absorbs these photons that come in from the sunlight in certain color ranges. Yeah, and then there is a process that takes place which converts. So not only the sunlight is required, you also need carbon dioxide. So carbon dioxide is present in some quantities in the atmosphere. Yes. So the carbon dioxide from the atmosphere and water from the soil. So the plants, they extract water out of the soil through the roots. They then the process of photosynthesis also needs carbon dioxide and sunlight, certain frequencies or wavelength of sunlight. So then what happens is there is a process that takes place which is not very well understood, which converts oxygen and water. Sorry, it converts. It takes water plus carbon dioxide plus energy from the sunlight, and that gives you glucose. So it is what is the chemical reaction like? It is six H2O plus six CO2, which gives you one molecule of glucose plus some extra oxygen is given out. Yeah, that's typically how it is. I'm sure it's all available online. You can look it up. So that's how it works. Uh, Now, how does this happen? Is a question. So the process of photosynthesis is something that happens with the help of certain proteins. There are certain proteins that act like antennas. They receive the photons. They take the photons, and then then the energy is passed into a molecular machine, essentially, within the plant's insides, yeah, within the cell. And this molecular machine operates at the molecular and atomic level, and we don't quite know how this works. And that's where the conversion of all of this happens, the chemical reaction happens. Now we can take photographs through via microscopes, electron microscopes or whatever, but it only shows you a photograph, a snapshot of a dynamic process. Now inside a plant, you have living material, right? These proteins are synthesized, they degrade, then the new protein is synthesized. This entire molecular machinery is something that is dynamic. It lasts for a while, then it degrades, and then it is replaced by something new. And this process is also very dynamic. It happens in an ongoing fashion. And even if we take photographs, or we take scanning, tunneling electron microscope images, we only see a snapshot of something that is a long process. So that's why we don't quite understand how it happens. And of course, this happens at the molecular and atomic level, which is the realm of quantum mechanics. So once again, we don't quite know how this happens, and that's the part where we don't quite understand, right? Because we don't have the means of peering deep inside and seeing things happen dynamically in real time at the atomic and molecular level. So that's where we don't quite know how it happens. Now photosynthesis itself is not a very efficient process. Of all the energy that's incident upon a plant leaf, I think about between 3 and 11% is actually utilized by the process of photosynthesis. More than 90% of the essentially 90% or more of the energy that's incident on the leaf is not utilized in photosynthesis. So it's not a very efficient process, and yet it's way more efficient than our solar panels and all that. So um, there's research ongoing into how to do artificial photosynthesis, because that would be great, because yeah. So now the second question is about solar panels. They take up too much space. Is it possible to just optimize plants to harness solar energy through artificial photosynthesis, this manner? Well, to do that, we would have to understand how the process works thoroughly. You need to understand how the process works, and you need to be able to replicate that in a repeatable manner. And we are not yet there, quite there yet, because we don't understand how it works at the uh, molecular and atomic level. We don't even understand the molecular reactor, essentially, which makes the process happen. So yeah, we are not there. If we can do I mean create a molecular machinery that can do artificial photosynthesis, that would be a great leap forward. Then you could have artificial plants, or bioengineered plants, or whatever it is, that could help us um, in some way harness solar energy more efficiently than how solar panels do it. So yeah, there is research that's ongoing in various parts of the world about possibly having a breakthrough and achieving the artificial photosynthesis, but we are not quite there yet. We are still quite a way far from there. And it's strange, because photosynthesis is what gave birth to life, essentially, on our planet. uh, if you look at the history of the earth, the first unambiguous evidence that we have of life, it dates back to about 3.77 billion years before today, right? The planet is about 4.5 billion years old. So around 3.77 billion years before today, you had the first life on the planet. And most of the original life, the earliest life, was photosynthetic life. You had cyanobacteria and various other unicellular organisms. Eventually they gave rise to multicellular organisms, and all of these relied on photosynthesis. And photosynthesis essentially takes the sunlight. It uses water and carbon dioxide to produce glucose and various carbohydrates, starches, and all that. And that's what sustains plants. And it is herbivorous animals that eat these plants, and they gain the energy which has essentially come from sunlight. And then you have carnivorous animals that eat those herbivorous animals, and that's where how the energy is transferred through these processes. So yeah, it would be great if you could achieve artificial, or discover how to do photosynthesis artificially, but we are not there. So long way to go for that to happen. Alpha says maybe life on Earth is an experiment. That's why they visit us to see the progress. Interesting, interesting conjecture you make here, my friend. So, what if life on Earth is an experiment? See, there are people. You know what they do? They create these artificial ecosystems. They take a big jar, they put soil in there, they put some plants in there, they put some, I don't know, earthworms or whatever, and some water. They seal this thing and they expose it to sunlight 12 hours a day or something like that, 8 hours a day or whatever. And such ecosystems can be kept sealed for decades. I remember I had seen somewhere a guy who had this closed sealed off ecosystem in a glass jar that was around for that was sealed for 60 plus years, and it was a thriving ecosystem. You had plants growing inside and you had some bugs and things like that, and generation upon generation of these plants and creatures, insects, etc., were growing and thriving in this closed sealed off ecosystem. Similarly, our planet, the Earth, is one such sealed off ecosystem. It's like a massive giant glass jar, yeah, sealed off by the vacuum of space. There is this atmosphere. We have this nice atmosphere that extends hundreds of kilometers. Well, the edge of space is technically defined as three as 100 kilometers above the surface, but that's how it is. So you have this atmosphere, you have a significant amount of water, and you have all this soil, topsoil, the Earth's crust, and all that. And there could be something going on beneath the surface of the Earth as well. This massive ecosystem, and it's been evolving for 4.5 billion years. Yeah. And life did emerge around 3.8, 3.77 billion years before today. So, what if somebody came from elsewhere and seeded life, put the seeds of life on our planet? There is a possibility that there is obviously the theory of panspermia, panspermia, that life was seeded on our planet from somewhere else. Maybe life, the seeds of life, exist throughout space, throughout the galaxy, throughout the universe, and once in a while they appear on a planet, maybe on an asteroid or comet, and that's the impact of the asteroid or comet that brings the seeds of life to the planet. And somehow that's how life is sparked off on planets that can sustain this sort of life, carbon based life. Yeah, that's a possibility. Or maybe there's an even more interesting possibility that maybe it is alien civilizations that want to seed planets and, you know, put the seeds of life on various planets. And maybe it's an experiment, and maybe we don't know they are there, but they are there and they're watching us, and sometimes they make their appearance and appear in the form of UFOs or whatever, right? Yeah, it is possible. It is possible. There's this famous science fiction book by Arthur C. Clarke. What is it called? 2001: A Space Odyssey. I think it's a trilogy or something, and I remember reading it a long time ago. And in the prologue of one of these things, there was this. Yeah, it was not a seeding of life, but it was the seeding of intelligence into apes. By exposing them to something or the other. Yeah, so it's a possibility, but do we have any evidence of that? We don't have any evidence of that. But you can't discount the possibility, even though the probability is quite low. It's still a non-zero probability. So maybe somebody from out there seeded life, maybe DNA. The DNA molecule is incredibly complex, and every single life form on Earth has DNA. So the common factor in all life on the planet is DNA. Yes, every single life form has a certain DNA. I mean, has DNA, and the DNA molecule differs. There are different sets of genes on each organism, which makes them different from each other. It's the genetic blueprint for that species. And yes, every single species, whether it's unicellular or multicellular or a higher life form or a very evolved life form like us, we all have DNA. We are essentially carriers of DNA. We are essentially living bags, and our singular purpose is to pass on the DNA from generation to generation. Yeah. So maybe we believe that our life's purpose is to, I don't know, whatever the purpose of life is, according to philosophers and whatnot, self-help experts and all that. But maybe the actual biological purpose of life is just to pass on DNA from one generation to another, and ensure that DNA survives. So maybe this DNA was seeded onto our planet by some alien life, by alien civilization. Possibility, it's non-zero. It's always a possibility. but the probability, obviously, it's remote because we don't have any evidence for this. So yes, there are all these conjectures, and maybe there could be some truth to some of these, but we don't quite know. Yeah, because we have never found any unambiguous evidence of aliens. Right, so that's what we can say about this matter as of now. Swapnil again. Researchers at the University of Glasgow recently suggested that water might have actually come from the most unlikely source of all, the sun. Hmm. Did water crash into the Earth from space by way of a massive comet, or was it around long before our planet's formation? Yes. So I am not aware of this recent piece of news. Rec- Recently suggested, okay, uh, that water might have actually come from the sun. Now let me try to think about how water could have come from the sun. The sun, as we know, it's mostly hydrogen and a little bit of helium and trace amounts of other elements. There is no way molecular water can survive there. So how would water could have come from the sun? What we do know is that the sun gives off this massive amount of solar wind. It expels all this plasma from its atmosphere. The sun has an atmosphere. It ejects this solar wind. Maybe the solar wind could interact with asteroids and comets and produce water. Is there a way it could happen? I don't know. I'll have to look at the research paper. So let me not try to speculate because I've not read it yet. Now, the question is, how did water appear on Earth? See, the solar system formed 4 point something, 4.5 or slightly more than that billion years ago from a protostellar disk, which is a disk-like structure, very very hot. Yeah, it coalesces slowly under its own gravity. At the center, you have the formation of a star, and nuclear fusion ignites. And then around the protostar, you have this big collection of debris that's swirling around, and that too coalesces under self gravitation, and that's how planets are formed. And sometimes you have collisions in the early solar system. Early stellar systems, you have various collisions until things stabilize a little bit, and then you have all these fields of debris. And the thing is this protostellar disk arises out of gas clouds that exist before a star is born. Now, these gas clouds typically come from the death of older stars. Yes, so the protostellar disk that gave rise to the solar system that we live in, it came from the death of a star that lived long before our sun existed. Yeah, so our sun is maybe a second generation or even third generation star. Yeah, now the gas disk or the gas cloud that existed and gave rise to our solar system typically would have come from the death of a star, older star, in the form of a supernova explosion. Supernova explosions, they give off lots of heavier elements. There's iron in there and all kinds of stuff, right? Now, what we do know is that so what we know is that everything we see around us, everything in our body, is star material, star stuff. It was all born inside it was all forged in the furnace of an ancient star. Everything inside our body, everything around us was forged in ancient stellar furnaces deep inside the nuclear fusion reaction. That's how it all came. And these old stars would have had planets, most likely, and water could have abounded on those planets. Yeah. So the material that gave birth to the solar system, it looks like there was a lot of water on it. Even today, when these asteroids, they crash onto the planet, especially a certain class of asteroid called carboniferous chondrites. I think that's what it's called. So if you take a cross section of these meteorites and you analyze them, you find that there is about 3 to 20% water in these meteorites, right? So what is believed, most popular uh, theory, the consensus theory, is that in the very early phase of the solar system, when the earth was very new, there was this massive bombardment on the earth, bombardment of ancient asteroids. Yes, and that is what brought in all the water of the earth. That's what gave earth its oceans. So all the water, or most of it, came from this asteroid bombardment. and some of it could have come from comets as well. Typically, if you look at the isotopic composition of comets, the deuterium to hydrogen ratio, uh, if you can analyze that or it in comets by taking by using spectrometers. So I think they had analyzed the deuterium to hydrogen ratio on various comets that passed by the Earth recently, 1990s and all that, comet Hale-Bopp, Hyakutake, etc. And they found that the deuterium to hydrogen ratio in those spectrometer readings was twice that you find on in the Earth's oceans. So that would indicate that if that is typical of most comets, then most likely it is not comets that gave us our water, right? Or maybe they gave us only a small amount of the water that we have. On the other hand, when you see when you analyze these the deuterium to hydrogen ratio on carboniferous chondrites, these meteorites, you find it very similar to that in the oceans of the Earth. So that is a strong indicator that most likely it is this carboniferous chondrites that bombarded the early Earth in very large numbers, and most likely it is these meteorites, this bombardment, this heavy bombardment that gave the Earth, its oceans, and all the water. Yeah. So that's what we know. We know there is water on comets. Comets are like dirty snowballs. A snowball, lots of ice, yeah, crystalline ice mixed with dust and things like that. So comets do have water, but asteroids also have water, and most likely the Earth's water came from asteroids, right? So that's what we know. That's the best theory that we have. Arjun Sinha says, how how does Cherenkov radiation make particles travel faster than light? It's it's the other way around. It is the traveling of particles faster than light within a certain medium that gives rise to Cherenkov radiation. So the Cherenkov radiation doesn't make particles travel faster than light. It is the faster than light travel of particles within a certain medium that gives off that causes this radiation to be emitted. Okay, let's take a look at Cherenkov radiation. What does it look like? It's a blue glow. Let me put that on the screen. Cherenkov radiation. What exactly is this? We'll get into it in a moment. So, Cherenkov radiation is typically something you see in nuclear reactors. Can you see this? This blue glow? Yes, blue glow again. It's typically this bluish glow in nuclear reactors, and that's what we call Cherenkov radiation. Now, what is this Cherenkov radiation? Does it make particles travel faster than light, or is it the faster than light travel of particles that gives off Cherenkov radiation? So, here's how it is. Uh, the speed limit in the universe is the speed of light, nearly 300,000 kilometers per second. Yes, that's the speed of light. Now, when it comes to so this is in outer space, in the vacuum of space. That's where light travels at this speed. But in other media, let's say the Earth's atmosphere, or glass, or water, in these media, light travels at a slower speed because of the interaction of the photons with the molecules of the medium, right? So in nuclear reactors, typically you have this reactor which is immersed in water for cooling purposes and so on, right? Now the nuclear fission reaction, that is typically what you see, that is not typically, that's always what you see in Earth, in nuclear reactors created by humans. The nuclear fission reaction gives off these energetic fast moving particles, and what you find is that these are very fast moving particles, and they break the speed of light limit in water. So light in water travels at 75% the speed of light in vacuum, approximately 75% of the speed of light in vacuum. But these energetic particles given off by the nuclear fission reaction, they travel faster than the speed of light in water, but they can't break the speed limit of light in vacuum. Okay, so understand that it's faster than the speed of light only in water. So this creates a shock wave, a conical shock wave of light that travels that comes after the particle has passed you by. It's like the shock wave. It's like the shock wave or sonic boom produced by an aircraft that's traveling faster than the speed of light in speed of sound in the atmosphere. Let's say you have a fighter plane. Let's say you're talking about the Tejas fighter plane, right? The Tejas fighter plane is a supersonic fighter plane. So it takes off, it flies in the air, and at some point in its travel, it goes supersonic. It crosses the Mach 1 limit. It crosses the sound barrier. So when this happens, the sound waves produced by the plane, they are trailing in the wake of the plane because the plane is for traveling faster than the speed of light, sound. So that produces this conical shock wave that hits you only after the plane is gone. So when the plane is coming towards you supersonically at the faster than the speed of sound, you hear nothing. It's only when the after the plane passes you by that you hear this shock wave, right? This big uh, shock wave. Let's see. I'm sure there is some illustration of that over here. Yeah, this is the kind of shock wave that you have. Yeah, there you go. Speed of sound, supersonic, and all that. So that is a sonic shock wave. Cherenkov radiation is the light equivalent of that sonic shock wave, right? So that is Cherenkov radiation. So let's say you have an electron that's passing through water faster than the speed of light in water. Then it will the interaction of this electron with the light with the water molecules gives off this very high energy, very high frequency radiation that is typically in the blue end of the spectrum, of the light spectrum. And when you have this process ongoing on a regular basis in a nuclear reactor, the entire water glows blue, right? So that is what Cherenkov radiation is. It doesn't make particles travel faster than light. It is the result of particles traveling faster than light in water or in any other medium. You can have a similar kind of effect in air also, I'm sure. Not that I know of it, but it's certainly possible. Yeah. So that is what Cherenkov radiation is. A very interesting effect. It is named after a Russian physicist, Mr. Cherenkov. Okay, Vinu says, what is the evidence for the Big Bang theory? How do we know the Big Bang happened? How do we know the universe is 13.7, 13.8, 13.77, whatever, 13.8 billion years old? Yeah. How do we know the Big Bang happened? What is the evidence for the Big Bang? So what's the evidence for the Big Bang? There are two pieces of evidence that make the most which are the strongest pieces of evidence. One is the CMB, the cosmic microwave background. That's radiation that is the afterglow, so-called, supposedly, of the Big Bang. And then you have the cosmological redshift distance relation, the Hubble relation, right? So these are the two pieces of evidence that provide the strongest support for the Big Bang theory. So what is the Big Bang theory? The Big Bang theory says that the universe originated as a point. In the very beginning, the universe was just a point. uh, you could call it the Big Bang singularity, and something made it expand, the space time within it expand, and that's what created the universe. So how do we know this? Why did people propose the Big Bang theory? So in the early 20th century, in the 1920s or so, Edwin Hubble, the American astronomer, he discovered that the universe is expanding, that the galaxies that we observe are all red shifted, which means that you have this Doppler effect kind of thing happening, and the galaxies are traveling away from us, and the expansion is actually accelerating, right? And that is the redshift distance relation, the Hubble constant. So if you if we know that the universe is expanding, the expansion is accelerating, then we can extrapolate that back in time. So right now, if the universe is getting bigger, in the past it would have been smaller and smaller. And if you calculate it, it gives you, and the calculations have been refined over the decades, and now we know that the universe began around almost 13.8 billion years before today. That is the best estimate or calculation that we have, right? Now, again, if the universe was infinite, almost infinitely dense, or maybe infinitely dense, and then it expanded, then you would have had certain properties that the universe would have had. For instance, in the very beginning, the universe was just pure energy, just pure energy. Then something called inflation happened, and inflation gave birth to mass. So the energy that was condensed in the form of mass. But even then, after the inflationary epoch, you had a very dense, very hot universe. So you had photons, and you had the very early uh, subatomic particles. You had this plasma in the universe. Now think about it this way. Think of the sun. We know the sun is a very hot, very hot ball of matter. Yeah, all hydrogen fusing into helium. That sort of fusion reaction is happening in the core of the sun. These photons are born out of the nuclear fusion reaction. All right, it gives off photons of light. These are actually gamma ray photons that are born in the core of the sun. Now when we think of the sun, we think of a very luminous object, very hot, very bright. But these photons that emerge from the sun, they take more than 100,000 years to travel from the core of the sun to the outside, and that's how they're emitted. So every single light photon that we observe has was born in the core of the sun, maybe 100,000 years ago, maybe a million or more years ago. It takes that long for that photon to journey out of the sun. Now imagine the universe as dense as the sun. It was at one point in time. So the photons had a very small mean free path. They were constantly bumping into these subatomic particles and all that, and there was no light, which means that inside the sun there is no light. The light is only outside the sun. The sun is luminous only outside. Inside the sun, it's all dark because the photons aren't able to move around. They're constantly being bumping into other particles and being emitted and reabsorbed and emitted and all that. So it's actually kind of dark inside the sun. It's only outside that it's shining and luminous. Uh, so the early universe was like that. It's only around about between 240 to 300,000 years before today, after the Big Bang, that the first light was able to emerge, when the universe cooled down sufficiently for hydrogen atoms to form, for them to capture electrons, and for stable hydrogen atoms to form. It's only then that photons became free to travel. And that's when you had the first light in the universe, right? So that's what the calculations tell us. That should have happened between 240,000 and 300,000 years after the Big Bang. So, if this theory is right, those photons should still be around. Yes. In the very beginning, the photons were very energetic, very hot. But as the universe expanded, if it happened, and is it expanded, it must have cooled down. So the photons would have been redshifted, stretched out, their wavelengths would have stretched out, and they would have lost energy. And according to the calculations, they should be now in the millimeter range, I believe, right? Millimeter range. So we do observe these photons, these cosmic microwave background photons. There was a Kobe experiment in the 1980s, 1980s, 1990s. Then there was a WMAP experiment, WMAP observatory, Wilkinson microwave anisotropy, whatever project or whatever it is. Yeah, WMAP. So this is a microwave. This is microwave radiation, not millimeter radiation, microwave radiation, and so on. Yeah. So then we had the Planck observatory, which was operational about a decade and a half or so ago. So all of these various experiments have demonstrated that the cosmic microwave background, the leftover afterglow of the first light of after the Big Bang, still exists. And it's very low temperature radiation. Its temperature is about 2.725 or something Kelvin, just a little bit above absolute zero. Yeah, very cold light. In the future, as the billions of years progress, it's going to get even colder. Yeah, it's going to lose even more energy because of redshifting and all. So all of these pieces of evidence tell us that the Big Bang actually happened. Otherwise, they would not see these things, right? So you have the cosmological redshift distance relation and the cosmic microwave background. So these two are the major pieces of evidence, yeah, that provide the strongest support for the Big Bang theory. There have been other theories. Dr. Jayan Narlikar had this theory called Hoyle-Narlikar theory, which was a form of steady state universe, that the universe is eternal and unchanging, that sort of thing. But well, the observational evidence doesn't support that. The observational evidence supports the Big Bang theory, what we call the Big Bang theory. So that, in brief, is the evidence. for the Big Bang theory. That's how we know that the Big Bang actually most likely happened, and that's how we know, because of the calculations, that the universe is approximately 13.7 billion years old. RTK says, there are some scientists who say that the Big Bang isn't the beginning of the universe. It's actually the end of some other universe. If it's true, does it mean that the previous universe was contracting at the rate at which the previous universe is expanding? Hmm. Um, See, the evidence, the observational evidence that we have is limited. It tells us that a Big Bang kind of thing would have happened. So based on all the evidence that we have, the best evidence that we have constructed this theory of the origin and the history of the universe, which we call the Big Bang cosmological theory, right? Um, so it says that in the past the universe was contracted into this tiny little point, the Big Bang singularity, and right now it's expanding. So yes, there are theories that say that maybe there was a universe before the Big Bang. Maybe there's a big bounce kind of thing. A universe expands and then starts contracting, and it contracts back into a point, so-called big crunch, but it just doesn't stay as a point. It bounces back again. So that's a big bounce. That's a kind of cyclical universe kind of thing. Yeah, and then you have the Roger Penrose theory of eons, cosmological eons. So. Uh, the expansion of the universe, it gives rise to the birth of a new universe, that sort of thing. Yeah, so we have these theories, but thus far these are just theories or just hypotheses, more or less, because a theory has to be falsifiable. A scientific theory has to be falsifiable, and thus far we don't have any means of either proving or disproving these theories, right? uh, I think Roger Penrose did give some kind of indication as to how one could test the theory. There could be ripples from an earlier universe left behind in our universe or something like that. But yeah, we are still far from doing that. But it is certainly a possibility. It is certainly a possibility that could have been our universe before our own. Yeah, every universe has a certain timeline, a certain lifetime, and eventually it either contracts again. The expansion after a point stops and it goes into a contraction kind of thing, and it goes back into the Big Bang singularity, and then it expands again. That's a possibility, but we don't know for sure. Yeah, so people are working on various theories, and if some evidence emerges, then one could take one of these theories more seriously than the others. uh, so yeah, some physicists speculate that the Big Bang isn't the beginning of the universe, but there is no proof thus far. But it's something that one should certainly consider seriously, because it certainly does fit into the laws of physics. Yeah, it's possible. Karthik Srinivas says, is HD 140283 Methuselah star older than the universe? Well, it's a star. Okay, what is this Methuselah star? It is a star that is located about 190 light years from here, from the Earth, from our solar system. So it's not really very far. It's essentially in our galactic neighborhood, in our corner of the galaxy, more or less. Yeah, it's not far. The galaxy is massive. Uh, so this star is somewhat blue shifted, which indicates that it's moving towards us rather than going away from us, and it's just 190 kilometers from 190 light years from the Earth. Now, so this star, I believe, has been known for a century or more, and various calculations have been done as to uh, figure out exactly how far it is from Earth using the parallax method and various other methods. And what we know is that this is a iron deficient star. Uh, This star has very low abundances of the heavier elements like iron, etc., which kind of indicates that it was formed in the very early universe when the heavier elements hadn't been formed. So how are the heavier elements formed? They are formed in the end stages or later stages of nuclear fusion in massive stars. But in the very early universe, you would not have had these massive stars. See, the first stars in the universe, uh, emerged when the universe was about 100 million years old. The first light in the universe was a quarter of a million years after the Big Bang. The first stars were born about 100 million years after the Big Bang, and the first galaxies came about 330 million years after the Big Bang. The oldest galaxy that has been found, it was discovered by the James Webb Space Telescope. It's called Glass Z13. It's believed to be about 330 million years. It was believed to have formed about 330 million years after the Big Bang. Now, so the first stars emerged 100 million years after the Big Bang, and it's only after these stars would have died that the heavier elements like iron, etc., would have been spewed out in supernova explosions into space, into interstellar space. And it's only the second generation stars that would have been richer in these heavier elements. So this star, the Methuselah star, is a star that is very deficient in heavy elements, which indicates it's one of the first stars to be born in the universe. And various calculations have shown that it's either 17 billion years old or 14 point something billion years old or 13.7 billion years old. So it's either older than the universe or as old as the universe. And that's a big mystery, because how can anything be older than the universe, especially when this star is part of our universe? So yeah, it is a big mystery, and thus far it has not been resolved. If you look at the star, it's kind of bluish. Let's take a look at what it looks like. Methuselah, Methuselah star. Methuselah. I don't know where these names come from, but whatever. Methuselah. What's it look like? It looks bluish. And why does it look bluish? Because it is blue shifted. It's kind of moving towards us. Yeah. So this is the star which is a great abiding mystery. All the calculations, and how do you calculate how old it is? You first have to figure out how far it is from the Earth, from the solar system. You do it through a variety of methods, and then you figure out the luminosity of the star, which kind of tells you, gives you various things. So that's how you calculate this thing, right? So the distance and luminosity tell you, of give you various indications about the star, the data. Yep. So this star is a big mystery. All the best calculations say that it's either older than the universe or as old as the universe. It certainly predates the first stars that were born in the universe. And why is it so? We still don't know. So it's one of the big mysteries in astronomy and astrophysics. And that's why it is the subject of significant research. Dr. Nishchay Gonge says, why shouldn't we look directly at a solar eclipse? Is it harmful in any way? Please comment about lunar eclipses as well. Okay, firstly, lunar eclipses and solar eclipses are very different. Yeah. What is a lunar eclipse? A lunar eclipse is when the Earth's shadow falls on the moon and completely eclipses it. So the entire moon goes black, goes dark, right? So that happens when the Earth comes between the sun and the moon, which is something that happens much more frequently than a solar eclipse. Yeah. So a lunar eclipse is essentially the Earth's shadow falling on the moon, which is when the Earth comes between the moon and the sun. That's a lunar eclipse. It's perfectly fine to look at a lunar eclipse. It's not going to hurt your eyes in any way whatsoever, right? So next time there's a lunar eclipse, go out there and take a look. Enjoy. It's fun to watch. Now, what's a solar eclipse? A solar eclipse is much more rarer. A solar eclipse is when the moon comes between where you are on the planet and the sun. So it is the moon's shadow falling on the Earth. Now, the moon's shadow is quite fast, so solar eclipse lasts only for a few minutes, and then the solar eclipse goes away. So if you are fortunate enough to be in the path of the totality of the eclipse, that's when you are able to see a full solar eclipse. Otherwise, you will only see a partial solar eclipse. Now, here's the thing. It is actually, be careful when I say this, and I request none of you to try it. But when you have the totality of the solar eclipse, when the sun is completely eclipsed by the moon, it's actually safe to look at it with naked eyes. Yeah. However, the problem with these solar eclipses is that they are very brief, and it may catch you by surprise that the moon suddenly moves out of the way and the full sunlight comes at you, right? So the sun's light is extremely bright. It's very harmful. um, as kids, I think most of us, we do this silly thing of trying to look at the sun. I surely did that. I certainly did that when I was a kid, less than 10 years old, looking at staring at the sun and trying to see if I can look at the sun. Yeah. And when you do that, you have this natural reflex of the eyes, try to close involuntarily. You may try to keep them open, but they close, right? They close at least halfway. So that shields you from the radiation of the sun. And secondly, the pupils of the eyes, they contract to pinpricks. So that ensures that very little sunlight comes into the eyes. So even as a kid, if you're trying to look at the sun, you have all these defense mechanisms, the protections that ensure that you don't suffer any real damage to your retina, because the sun's light, the radiation is extremely intense, very bright. It can destroy the retina that's behind the eye, right behind the pupil of the eye, at the other side of the eyeball. And if you do that, you're going to have permanent damage. Now when you're looking at the solar eclipse, and let's say it's a full solar eclipse, so the sun has gone completely dark. If you're doing that, then first of all, your eyes are not squeezed half shut like that. And secondly, your pupils are fully open. They're fully open. They're allowing the maximum amount of light to go into your retina. And then, if by the moon surprises you and just moves out of the way, and you're the first rays of light coming out of the sun full stream, then you will find yourself caught unawares. Your eyes are fully open and your pupils are fully dilated, and they are allowing the maximum amount of light to come in. And that's when you will suffer permanent damage in your retina. It may cause blindness or partial blindness. You don't want that to happen, right? So that's how it is. So even though it is safe for a few minutes to look at the completely occluded sun when the solar eclipse is full, not partial, it is still highly dangerous and completely unadvisable to do that. So either look at a solar eclipse by seeing the reflection of the sun. In There are a variety of ways of doing it, but if you're actually going to stare at the sun with your own eyes, you need to use those dark glasses or whatever the standard equipment, the standard equipment that is provided for seeing a solar eclipse. That's typically very thick dark glasses, right? So that's what happens. The sun's rays are extremely energetic, very bright. There's a whole spectrum of radiation that comes in, the far infrared light also, which is almost like ionizing radiation and all that. So all of that is going to destroy your eyes if you try to do this. So please don't do it. Please do not do it at all. Don't ever try it. Alpha Beta says, why do wrinkles appear? Can we be old without having wrinkles too? Wrinkles appear on human beings' skin. It's the because of the process of aging. So if you have an infant, the skin is very very flexible, very very soft, yeah, and very healthy. But as a human being ages, past a certain age, the wrinkles appear because of a number of reasons. First of all, the skin becomes less flexible, less stretchable. That is number one. Secondly, the natural oils that the skin typically uh, gives off. The skin, especially the face, is typically a little bit oily, right? Some people have more oily skin, some people have less oily skin, but the skin, it gives off these natural oils, and that also contributes to keeping the skin flexible, stretchable, and healthy and young. So as a person ages, firstly, the flexibility of the skin decreases. Secondly, the amount of oil that is emitted by the skin, that also decreases. And thirdly, the amount of fat that is below the surface of the skin, that also kind of decreases. So all of these factors contribute to these wrinkles appearing on not just a person's face, but the hands and whatever else, right? So yeah, that's how it happens. It's all because of the process of aging. Now, the process of aging, how it happens, it is believed to be because of the shortening of the telomeres at the ends of your chromosomes. So inside your cells, not the red blood cells but the other cells, you have these chromosomes that contain your genetic blueprint, the DNA, right? And at the ends of the chromosomes you have something called telomeres. So these telomeres, as the cell division happens again and again and again and again, which is natural in a healthy body, every time cell division happens, the telomeres are shortened a little bit. And it is believed that the shortening of the telomeres at the ends of the chromosomes, that is what contributes to the process of aging, right? And there is all this research that's happening into how to reverse, or either reverse, or at least stop the lengthening of the telomeres. And that could possibly uh, help ward off aging or delay aging, at least. Yeah, that's the kind of research, that's the hope that these researchers have. I mean, who doesn't want to live forever, or at least live to 150 or 200, right? That would be great, some people think. So yeah. So anyway, the wrinkles, they appear because of these reasons. Not the maybe the telomere lengthening or shortening actually could contribute to it. But over time, as the years go by, the flexibility and stretchability of the skin decreases. It becomes more brittle. The amount of oil that's exuded by the skin also decreases. That also contributes to more brittleness and more inflexibility of the skin. And the amount of fat that's at the subcutaneous level also decreases. And all of these factors contribute to the appearance of wrinkles, which become more pronounced with age, right? That's the natural progression of how wrinkles appear on people's skin. So the question is, can we be old without having wrinkles? I have no idea. I don't know. It's part of aging, so it's just how it is. So maybe in the future, scientists will invent some mechanism by which the aging process could be slowed down, or stopped altogether, or maybe even reversed. Who knows? Maybe there'll be some skin oil, skin cream, or maybe some tablet to take, or some gene therapy or whatever. So yeah, in the future, this sort of thing may happen. But as of today, I don't think it's possible to get old without having wrinkles. Uh, every person who ages will develop some amount of wrinkles, I suppose. Yeah, that's just how it is. Swapnil again. What are brine pools? How are they made, and where are they located in the oceans? If sea creatures are able to survive in them, could it give astrobiologists a hint on how life could thrive on other worlds? Okay, let's see what brine pools look like. Okay, first of all, what are brine pools? To answer what are brine pools, we must first answer what is brine. So, brine is seawater with a very high degree of salinity. I think, what is the typical salinity percentage of seawater? 3% salt? Not sure. Okay, don't quote me on that. But typically, brine is seawater with 10 times that much salinity. So if on average seawater has 3% salt, 3 ppm of salt, then brine could have 30 ppm of salt, or maybe more than that, maybe 50. So it's very concentrated and very saline. Yeah. Its salinity is way higher than your typical regular salt water in the oceans. So that is brine. So what are brine pools? These are regions in the ocean, at the bottom of the oceans, where you have a collection of brine. So brine is this water with extremely high salinity, much higher than the rest of the ocean. And because of the extremely high salinity, it is much denser than ocean water. And that's why it congregates in one place, and it forms these pools that create indentations on the ocean floors. So it's like a lake. It's like a lake on the ocean floor, a lake of brine on the ocean floor, right? So let's take a look at what these things look like. If we have examples. Brine pool. Let's see what a brine pool looks like, and let's put that on the screen image. Okay, here's an example of a brine pool. As you can see, it's like a lake on the bottom of the ocean. Underwater lakes of despair, they're called. So these are lakes, and they actually look like craters because the brine is much denser, and therefore it creates these depressions on the ocean floor. And yeah, you can look at you can see the color is different, and it just looks different from regular ocean water. Now, one of the things about brine, first of all, we know it's extremely saline. Its salinity is very high. Secondly, it also is anoxic. So because of the extreme salinity, the water also becomes anoxic. What is anoxic water? It means water with very little dissolved oxygen. So if you see various kinds of marine life, whether it is fish, whether it is crustaceans, crabs, lobsters, prawns, shrimps, whatever, they all live by extracting the dissolved oxygen out of the ocean water, and they do it through these organs called gills, right? Gills. Now, if an organism like, let's say, a crab or a fish were to go and swim into a brine pool, they would immediately find that there is very little oxygen here, and the salinity is very high. And if they stay there for more than a few seconds, they will go into hypoxia, which means that brain will stop receiving oxygen and they will die. So typically you find lots of dead animals, marine animals, fish, crustaceans, etc., inside brine pools, and that's why they call them these pools of despair or whatever. So any sea animal, sea creature that goes into it will almost instantaneously die. So that is what you have in brine pools. But on the edges of these brine pools, you have certain kinds of life, certain organisms that are called extremophiles. Yeah. That undergo chemosynthesis. So we have photosynthesis, in which light is used to create various forms of energy, chemical energy. Yeah. So chemosynthesis is when this sort of reaction happens without the need for light. That's chemosynthesis. So you have these extremophile animals that can live on the edges of brine pools, but not inside brine pools, right? So that's what it is. So the question is, how do these brine pools, how are they made? How do they form? I believe how brine pools are formed. How is brine formed inside oceans? I think it happens in cold regions of the ocean. So when uh, on the surface of the ocean, when you have very low temperatures, below freezing temperatures, that's when the ocean waters freeze. You have the formation of icebergs and ice sheets, etc. Right? In the polar and Antarctic regions of the Earth, and in cold latitudes, yes, you have this happening. So when water freezes and becomes ice, the salt molecules aren't able to become a part of the crystalline ice structure, the ice crystals. So there is this process called salt rejection, I think. So when the water freezes, salt is rejected. So these ice structures, they are less saline than the actual ice, the actual ocean water. So all of this salt that is rejected, it goes back into the ocean and it forms brine. And that's how the brine is formed, and that's how then the brine is denser than the ocean water. That's why it sinks to the bottom of the oceans. And in some places you have the big collections of brine, and that's what these brine pools are. So yeah, that's the answer. And if sea creatures are able to survive in them, could it give astrobiologists a hint on how life could thrive on other worlds? Possibly, possibly. Yeah, astrobiologists are always on the lookout for strange forms of life on our planet. Uh, we have various extremophile organisms, such as at deep sea vents, when you have these essentially these volcanic openings on the sea floor, which give rise to very strange biology in those regions. Yeah, life that can thrive without sunlight, extremophile life. So similarly, around brine pools, we have these organisms that undergo chemosynthesis. Yeah, these are also extremophile creatures. That also could give some hints as to how what kind of life could thrive in extreme environments. Yeah, so certainly something that they would want to study. Pulkit says, how is a black hole formed? Do you think there's a possible end to it, or is it just like a space animal with never ending hunger? If there's any, what impact could it create in space in the last stages of its death? Okay, how is a black hole formed? Your typical regular stellar mass black holes, they are formed at the end stage of a supernova eruption explosion. Yeah. So let's say you have this massive star. Let's say it's 20 times the mass of the sun, 50 times the mass of the sun, massive star. It in the end stage, it collapses upon itself. Yeah. And this collapse gives rise to an explosion, the supernova explosion. But at the very core of the star, you're going to have these crushing gravitational forces that will repel any of the electron degeneracy pressure or any other thing that can, you know, keep it off. And that's how it causes this collapse of the star, a region of over density that is too dense for even light to escape. And that's what creates a black hole. That's what gives rise to a black hole. In some cases, we find that stars possibly collapse into black holes without ever reaching the supernova stage. There are these old star maps, star images that are taken over the decades, and sometimes we find that stars have just disappeared. Stars that were shining, let's say in the 1970s, 1980s, today, if you look at the same part of the sky, that star no longer is there. It's just winked off. Yeah. So maybe it's a star that collapsed directly into a black hole. So typically it's because of this. Yeah. The end stage of a star's life, or actually the end stage of a star's death. That's what gives rise to a black hole, when the star, the nuclear fusion reaction is no longer able to continue, and the entire mass of the star collapses upon its core. That is the core collapse. Typically there's a supernova, but sometimes by some reaction, by some mechanism, you may have collapsed directly into a black hole. So that is your typical stellar mass black hole. That's how it is formed. um, Supermassive black holes, we don't quite know how they are formed, because for a black hole to become that large, it would take a time that is longer than the actual age of the universe. So supermassive black holes, the formation mechanism is kind of a mystery. You typically have a supermassive black hole at the center of every galaxy. Most galaxies, our own galaxy, has a massive supermassive black hole at its center, uh, and so on. So how they are formed, they it is speculated that they it was primordial black holes that formed the seeds of supermassive black holes. That's a possibility. So what are these primordial black holes? Primordial black holes are black holes that could have formed in the very early universe as regions of over densities. Yeah. Because of quantum fluctuations in the very early universe. So those would be typically microscopic black holes, MBH or PBH, primordial black holes. uh, and it's possible that they could be a significant component of dark matter today. Yeah. In various forms. So that's how a black hole is formed. Is it possible there's an end to black holes? Yes. Black holes have temperature. They are thermodynamic objects, and anything that has a temperature radiates. It radiates radiation. So black holes radiate black body radiation, and black holes have a temperature. That's why they radiate. Um, and this radiation is called Hawking radiation, and it's essentially like a process of evaporation. Yeah. And because of that, black holes typically become smaller over time as they evaporate away their mass energy. So the black holes, any black hole's temperature is inversely proportional to its size. The larger the surface area, the lower the temperature. So supermassive black holes are typically extremely cold, even colder than the uh, temperature of the cosmic microwave background radiation. So in a sense, supermassive black holes can never die, because they're actually accreting mass rather than emitting radiation, because they are at a temperature that's lower than the ambient temperature. But smaller black holes are hotter, and they would emit Hawking radiation, which says that every black hole has a certain lifespan. You can calculate the lifespan quite easily, actually, if you know the physics. Yeah. So every black hole has a certain lifespan. You can calculate that. And eventually, as the black hole becomes smaller, it becomes hotter. As it becomes hotter, it radiates faster. It becomes even smaller. So the end stage of a black hole's life is a massive explosion. Boom. So black holes die in explosions. That's what the theory tells us. We have never seen these explosions thus far, but it's possible that it is the end stage eruption or explosion of the Hawking radiation of a black hole's end stage life that could be the 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 progenitor of certain classes of ultra high energy cosmic rays. It's possible. It is indeed a possibility. So that's the kind of uh, life cycle a black hole has, there is certainly a possible end to black holes in their lives. Yeah. So yeah, so what impact would it create in space at the last stages of its death? It would be a big flash of radiation, flash of light, and things spewing out of it at relativistic velocities. It could be possibly something that gives rise to the gamma ray bursts, possibly short-lived gamma ray bursts, and so on. Yeah. Avinash Singh says, if I enter into a black hole, if I enter a black hole, will the time stop for me as soon as I cross the event horizon? Or does the time stop after I reach or when I reach the singularity? If time stops just after crossing the event horizon, does it mean wouldn't it mean that I'll be stuck at the event horizon and will not reach the singularity, because when time stops, nothing can move from its place? Okay, what happens? So we have to understand time dilation, which is an effect of relativity. Time dilation is something you study when you're studying special relativity, but it's something that you experience because of mass and velocity and all that. So the concept is very simple. The faster you go, the slower your time is. But you will not sense time slowing down. For you, time goes on the same. Let's say you have two brothers, twin brothers. One is on Earth and one goes into space on a rocket. Yeah, at a relativistic velocity. Let's say half the speed of light. Yeah. So we put two identical clocks with these two twins, the same clock. One with the twin on the rocket and one with the twin on the Earth. And our friend on the rocket, he goes away and he has this clock which tells him that 1 year has elapsed, and then after 1 year is elapsed he comes back to the earth, and he will find that maybe 30 or 40 years on earth have elapsed. So for him only 1 year went by, but for his twin on earth 30 or 40 years had elapsed in the same time. So the clocks move differently. The rate at which time flows in the rocket is different from the rate at which time flows on the earth. It's very confusing, but it's actually quite simple. So so if you are on earth, you will see that the time on the rocket is flowing very slowly as the rocket is going very fast. Now let's say you are falling into a black hole. Yeah. Let's say you have two observers. Let's say you have two human beings. One human being is at a distance of, let's say, 1,000 kilometers from the black hole, in orbit around the black hole. So this person is in no danger of falling into the black hole, so he can observe what's happening. The other person, which is you, my dear friend, you're going into the black hole. So let's say your friend is in orbit around the black hole. He's not falling, but he's going to observe what happens to you, and you are falling into the black hole. Now the presence of mass also slows time down. So the closer you come to the black hole, the slower your time is. If you're wearing a watch, for you the time will pass just normally, but your friend who is sitting far away will see your progress towards the black hole slow down. And when you reach the event horizon, you for your friend who is sitting far away, you will appear to have frozen in time. He will never see you enter the black hole. For your friend who is sitting far away, you will seem like you have just become stuck to the event horizon and you're not going anywhere further from there. But you actually will enter the event horizon and you will go into the black hole. Yeah. So for you, time doesn't stop or time doesn't slow down, but from the perspective of a distant observer, you will slowly stop at the event horizon. Now what happens to you when you come inside the event horizon? So once you enter once you cross the event horizon and you move towards the singularity, it I think you will experience all the future time of the universe until the end of the universe. So before you reach the singularity, you will experience all the future events or something like that. Yeah. So it's not very well understood yet, but yeah, it's kind of like that. Of course, before that you will die because you will be stretched out into a spaghetti kind of thing. So so only in case you have an indestructible consciousness will you be able to experience future time and all that. It's very weird and it's still not very well understood, because as you go deeper towards the singularity, the mathematics of general relativity breaks down and you have a singularity, yeah, because which obviously should not exist because it is unphysical. Anyhow, that's how it is. So for you who is entering the black hole, time doesn't stop, time doesn't even slow down. For you it's just a few minutes and you're in. And the smaller the black hole, the more the spaghettification. If it's a supermassive black hole, you will feel nothing as you enter the event, as you cross the event horizon. But if it is a smaller black hole, long before you cross the event horizon, you will be stretched out into spaghetti and you would have died. It's not a nice death. So that's how it is. Dungar Singh Chauhan says, why is a black hole called a hole? It's just a mountain of matter crushed into a tiny space. Should they be renamed? You know what? You can go ahead and rename it to whatever you want. These names, black hole, Big Bang Theory, these are not scientific names. Typically, these names are coined by non-science people, typically by journalists. I think the term black hole was coined, if I'm not mistaken, by some journalist, and then it stuck. The term stuck, and then even scientists, physicists started using it, and now that's what we call them. It's not really a hole, right? It's a, well, it's a region of space that is so dense that light can't exit from it. So it's not a hole. It's just pure mass essentially. Yeah, so it should not be called a hole. It's incorrect to call it a hole in space time or whatever. So you want to rename it, you can go ahead and call it by some other name if you wish to. But it's the name that is stuck because it is so catchy. Black hole, yeah. And similarly, Big Bang Theory was actually a pejorative name. I think it was coined by Fred Hoyle, if I'm not mistaken, to make fun of this theory, which was so outlandish. So he coined this term Big Bang to make fun of the theory as a means of disrespecting the theory. But it kind of stuck, and then this theory took off because it makes a lot of sense from all the observational evidence that we have. So now it's called the Big Bang Theory, even though it was not a bang or an explosion. It was not an explosion. It was an expansion of space-time. So that's how it is. Sometimes you have all these weird unscientific terms that stick, and then even scientists start using them. Yeah. So yeah, if you want to rename black hole to something more appropriate, you can go ahead and do that. And if it is catchy enough, it may catch on. Okay, Dash Plays says, does light bend towards the gravity, or does every wavelength of light bend towards gravity? Um, Light and gravity has this. See, what happens is this: mass curves space-time, curvature. We live in four-dimensional space-time. We experience the three dimensions of space: top, down, uh, up, down, backward, forward, and whatever. Right? Three dimensions of space time. This way, the three-dimensional coordinate geometry that we experience in the real world. There's a fourth dimension, which is time, which we experience very vaguely. So these four dimensions, they form the fabric of space-time. We cannot imagine four-dimensional space-time. We can only imagine the world in three dimensions. But space-time is in four dimensions. Now, if you have a mass, let's say a planet or a star, that is going to warp and curve space-time. We know the typical trampoline image that they show us, right? Curved space-time. Let me see. Curved space-time. Yeah, the typical image that they show you to illustrate how this works. Let me show you that. 1 second. Let me put that on the screen. Curved space-time. So you know how it is, right? It's like a trampoline on which you put a mass, a ball, and that curves the trampoline surface, and that is the curvature of space-time, which actually doesn't make much sense because you're seeing space-time as a two-dimensional thing. A better way of visualizing this is by looking at this image. Let me show you that. So this is the actual curvature of space-time, right? The entire four you seeing curvature of space-time in three dimensions here. It's actually four dimensions, which you cannot visualize, but this is a better way of looking at it. So the presence of mass curves and warps the fabric of space-time itself. Now, if you have a beam of light that is traveling straight, but then you have this mass sitting there, which you can see there, 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 yeah, then the beam of light will not be able to travel in a straight line. It will travel in a curved path because the space itself is curved, right? And the time itself is curved. So that's why gravity bends the path of light. And yes, every wavelength of light is bent. It doesn't matter what wavelength the light has, it is all bent because the path itself is curved. Let's say, imagine that the light is like a car traveling on a road. If the road is straight, the light will the car will travel straight. But if the road is curved, then the car will have to travel in a curved path. That's how it is. Yeah. So light is bent by gravity because space time itself is warped, it is curved, it is bent by gravity. And yes, every wavelength of light is curved, is bent. Its path is bent by gravity. Dash plays again. Does gravity of antimatter re- okay, what is asking is, does antimatter have repulsive gravity? Right? That's what is asking. So you have two kinds of matter. You have regular matter that we are made of, yeah, and you have antimatter. So the question is, does antimatter have repulsive gravity or negative gravity? Which means that instead of falling up, it should fall down. No, that is not the case because we have manufactured very, very small, tiny quantities of antimatter in labs, yeah, in various colliders, etc. And it behaves gravitationally just the same as regular matter. So unfortunately, antimatter doesn't have the interesting property of having repulsive gravity. It just has regular gravity. Repulsive gravity, we haven't found any substance that has that property. Yeah, negative negative mass or something like that. Yeah, we still haven't found that. Avinash says, if a distant solar system is millions of light years away, and so we see it as it was millions of years ago, how can we see what it looks like now? Simple answer, we can't see what it looks like now. Impossible. Simply can't happen. Won't happen ever. Unless you sit on a spacecraft, you travel all the way there, and then once you are there, you can see how it is right now for your right now. But for us over here, it will be different. Yeah. So you have this Methuselah star, which is 190 light years away. So what we see of it is what was happening 190 years ago. Yeah. So there is absolutely no way of seeing what it looks like right now. And the concept of now doesn't really make sense in relativity. There is the relativity of simultaneity, which is a whole different thing. So an event, let's say two events occur simultaneously to me, but for somebody else large distance away, those two events may not appear to be simultaneous. That is also a thing. So now itself doesn't make a lot of sense from the perspective of general relativity. Yeah, the concept of now. So yeah, there's no way for us sitting here to see what something looks like right now if it is millions of light years away. Simply not possible. Simply. Okay, Vinu says, what are cosmic strings? What is their relationship with wormholes? Cosmic strings are hypothetical, no, theoretical defects in the fabric of space-time. They are called topological defects, and they may have been the result of the expansion of space-time in the aftermath of what we call the Big Bang. So these topological defects could have been produced in great quantities in the very early universe. So what do I mean by a topological defect? Yeah, a defect in the fabric of space-time. It's like a wrinkle in space-time. We spoke about some time ago wrinkles on people's skin. Yeah, wrinkles are these deformities or malformations on the smooth surface of the skin. The skin is no longer smooth, it has these wrinkles. Yeah, similarly space-time, the fabric of space-time, the four-dimensional space-time, that itself could have had wrinkles that formed in the very early universe. So, what would be the property of such a wrinkle, such a cosmic string? See, it's like this. Let's say I put my finger over here and I travel all the way around, yeah, and come back to the same point. I will travel a full 360 degrees. Yes, we know that's what geometry teaches us in school. Yeah. So you take a pencil, a finger, or whatever, you go all the way around and come back to the initial point. You will traverse a full 360 degrees. Let's say you have a cosmic string. Let's say you encounter a cosmic string, yes, and you try to go all the way around. So you go there, you start at an initial point, you travel all the way around, and you reach back at the original initial point. You will find that you have traveled less than 360 degrees. That is a defect in the fabric of space time itself. Yeah, it's going to break all the laws of geometry and everything. So that's what it is. It is these cosmic strings are supposed to be extremely thin. Yeah, and they could go on to, up to the ends of the universe, so almost infinitely long. If the universe is, I mean, they would extend beyond the observable universe, and as the universe expands, they also get stretched thinner and thinner, but they don't break. So these are the topological defects that could have formed in the very early universe. You could have had very large amounts of numbers of cosmic strings, but as the universe expands, they would become further and further spread apart, and maybe it's very hard to observe it. Now, cosmic strings, if they exist, they would be gravitationally massive. They would warp uh, space time, so they could create gravitational lensing. So that could be one way of detecting them. Second, so they would have these gravitational effects. They could create gravitational lensing. um, and yeah, there would be these defects in space time. So if you go around them, you would end up traversing less than 360 degrees. So that's what cosmic strings are. People have been searching for them. Nobody has found them yet. But yeah, it doesn't mean they don't exist. It means that it, if they do exist, they could be so rare, and the space is so massive that it would be very hard to detect them. Now, what is the relationship between cosmic strings and wormholes? No relationship, actually. No relationship. But the thing about wormholes is this: if you want to construct or create a wormhole, which is a hole in the fabric of space time itself, it could be a hypothetical way of allowing people, allowing someone to travel vast distances through a shortcut called a wormhole. So a wormhole is something that is a solution to Einstein's equations of general relativity. The thing about wormholes is that they want to snap shut. So wormholes have an opening, two openings, and a neck. This neck wants to snap shut immediately. Yeah, and the point at which it snapshots will be a black hole. That's how it is. So it's very hard to keep a wormhole open. To keep a wormhole open, you would need some exotic matter in the throat of the wormhole, something like negative mass, which would have a repulsive form of gravity, which would keep the wormhole's throat open and won't allow it to snap shut. Or you could thread a cosmic string through a wormhole, and that would prevent the wormhole from closing. So that way, you could engineer a wormhole that stays open if you know where a cosmic string is, and you can acquire it and you can thread it through a wormhole's throat. Yeah. So that is one way in which you could have a traversable wormhole. But then obviously you will have to deal with the gravitational effects of the cosmic string and the very strange properties that it has of having these, less than 360-degree travel through it and all around it and all that. Yeah. So yeah, that in brief is what cosmic strings are. Dash plays again. Wow, today is Dash plays day. So the question is, hypothetically, if we have an indestructible container with a hole continually getting filled with hydrogen, with more increasing pressure that's forming inside, what will happen? Will hydrogen turn to helium and future more? If yes, what happens to remaining protons and neutrons? All right. So what you are proposing here, my dear friend, is a thought experiment, a Radankian experiment. So we don't have to build this indestructible container and fill it with hydrogen and keep filling it. We can do this experiment purely in our thoughts. We know the laws of physics, so let's see what happens. So let's say you have this magical container that is indestructible. Nothing can destroy it. And it has a fixed diameter, fixed radius. Yeah, you, no matter how much pressure it has inside, it won't change. The radius won't change. It won't break or whatever. So let's say you have this indestructible container. You start filling it. You start pumping in hydrogen gas. So as more and more hydrogen molecules get inside, hydrogen atoms go inside. Yeah, the pressure inside the chamber container will increase. As the pressure increases, you're going to have an increase, corresponding increase of temperature. So the pressure keeps on increasing, the temperature also keeps on increasing, and the density keeps on increasing. Eventually, at some point in time, you will have a density which is similar to the density inside the sun. That's when you will have nuclear fusion, which will ignite. If you have a density similar to the density of the sun, you will also have a temperature similar to that of the sun. And these conditions, as you keep on pumping in more hydrogen gas, these conditions will ignite nuclear fusion of hydrogen into helium. And if you keep on pumping more and more and more hydrogen gas, you're going to have a star inside. The ignition of fusion itself is the formation of a star. Yep. And if you pump in more and more hydrogen, you're going to have more and more fuel that gets converted into helium. And eventually all the hydrogen will get converted into helium, and if you pour more hydrogen in, um, eventually you could have a proper stellar uh, cycle. You know, as the pressure keeps on increasing, the helium itself will undergo fusion and give rise to heavier and heavier elements, and that sort of thing will go on. So yeah, that's an interesting thought experiment. That's how you can create a star. If you have this sort of container, you can create a star within it. Yeah. What happens to remaining protons and neutrons? Well, the remaining protons and neutrons will be part of these newer elements. And eventually, if you just keep on pumping in hydrogen indefinitely, you will have so much density that this whole thing becomes a black hole. And then we don't know what's inside. Yeah. And if it becomes a black hole, it may eat up your indestructible container too, because I think black holes can eat even that. So, yeah, that seems to be the end stage of this thought experiment. Interesting thought experiment. Good imagination. I like it. Karthik says, "Is our universe created from nothing?" Well, we don't know. We had another question about what came before the universe, right? So we don't know what came before the universe. Was Is the universe part of a bigger multiverse kind of thing? Yeah, is it so? What came before the Big Bang? Was there an older universe before this universe? Are we living in a cyclic universe? Do we have a big crunch and a big bounce kind of thing? A big bounce could happen because of LQG, loop quantum gravity. Um, is our universe a simulation? That is also a possibility. Yeah, it's not impossible. It's certainly plausible. It would not break any of the laws of physics or anything we know. So yeah, we don't have the answers to these very big questions. There are very big questions that are being asked over here. What came before the universe? What were the ingredients from which our universe was constructed and created? We don't know. We know that the universe at the very beginning was just this singularity kind of thing, infinitely small, infinitely dense, infinitely hot, and the space time and pure energy inside. Yeah, just pure energy. Then space time expanded for whatever reason. We don't know what triggered that off, but the expansion happened, inflation happened. Then you had the formation of mass, coalescence of mass out of energy, and then the whole history of the universe. But what happened before that? What was there before the universe? We don't know. We don't have the answers. Maybe someday we may have the answers, some answers. Maybe we won't. We don't know. But yeah, we don't have the answers to these questions. But these are good questions that drive us forward and keep us curious. Dr. Nishchay Ghonge says, "Why do the masses struggle with math and physics? Any special reason for that?" Uh, yeah, typically the scariest subjects in school, college, etc., are math and physics. Math is scary because you have to solve these difficult problems, and physics is scary because it uses math. Without math you can't do physics. So these are the two scariest subjects. Now, so the real question is, why is math so difficult? Why is math so scary? If math were easy, physics would not be easy, would not be difficult either. So the reason why masses struggle with math, math is the simplest and easiest thing in the world, but it has to be taught properly. The reason why most people struggle with math is because teachers teach you something and they assume that you have understood everything. Most teachers are mediocre teachers. They don't know how to explain things simply. The key to teaching, I believe, is to make things as simple as possible. A teacher should not try to show off how intelligent and how brilliant they are. They have to keep things as simple as is humanly possible and teach it in that manner, and make sure that the recipient, the student, is actually understanding what is being taught. Most teachers are like, repeat after me, this is what I write on the blackboard, you copy it down, and now you start solving problems. And they don't care whether the student has understood what has they've been trying to teach. I remember as a kid myself, I had this terrible teacher. I don't know what standard I was in, third standard, fourth standard. I was learning decimals, decimal places and all. And you have these problems in which you have to do additions of numbers with decimal places. And I clearly had not understood what decimals are, because the answer which I gave had two or three different decimal places, 3.1.2.3 or something like that. You know, Eventually I got it right through self study. Yeah. So that's how it is. These simple concepts have to be explained clearly and properly. If you don't do it, the student won't understand it. And then they will try to memorize things. You don't memorize things in mathematics. You understand things conceptually. And then more advanced concepts are built on top of the simpler concepts. And if you don't understand the simpler concepts themselves, then how are you ever going to understand the more advanced concepts? So if you don't understand fractions, you don't understand decimals, then how are you ever going to understand trigonometry or algebra? Yeah. And then how are you ever going to understand higher concepts like things like calculus and matrices and linear algebra and whatnot? So if you don't have the fundamentals down clearly, there is no way you can understand higher mathematics. And it is always because of bad instruction, poor teaching, that the fundamentals are shaky in most people. Yeah. So that's why the masses struggle with math and physics, because of bad teaching, because of bad teachers. I believe anybody can master mathematics. Mathematics is just pure logic. It's the simplest and easiest thing in the world, provided it is taught properly and the foundations are built properly. Then you can study, then you can learn any kind of mathematics. And if you are good at math, well, you're going to be good at physics. It's just a given. So the special reason why the masses struggle with math and physics is because most teachers, 95% of teachers are very poor, mediocre, and they don't care whether the students learn or not. And they are not able to communicate effectively and teach effectively. And they don't ensure that they take the feedback from the students, whether the students understood or not. And they just go on forward and forward. And that's why this happens. Karan says, how to deal with harder topics in mathematics. To deal with harder topics in mathematics, ensure that you have mastered the simpler topics. Right? If you master the simpler topics, if you master the fundamentals, the basics, then you will have no great trouble mastering the topics that build on top of that. Yeah. So if you want to understand multiplication, you have to first master addition and maybe subtraction as well. Because what is multiplication? It is repeated addition. What is 3 times 8? It is you take 3 and you add it, keep on adding 3 8 times. That's 3 times 8. So to understand multiplication, you have to first properly master addition. Then once you do multiplication, then you can go into division and things like that, and so on and so forth. So to deal with harder topics in mathematics, you have to ensure that your fundamentals, your basics are very, very clear. You've mastered it thoroughly. Then you can move on to harder topics. Of course, eventually you will reach a stage where even the best fundamentals and all that will not be able to help you master certain topics, because eventually mathematics becomes really abstract and most people can't deal with that. Only genius level mathematicians can deal with certain kinds of mathematics, right? Ramanujans and John Nashes and all that. So, but most people don't need to understand mathematics at that level. So the simplest thing is master the basics, master the fundamentals. How do you master that? Problem solving. Solve hundreds of problems, thousands of problems. Yeah, that's it. Done. Solemn Viz says it's believed that India's very own Area 51 is the Kongka La Pass on the border of mm, 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 on the line of actual control between India and Chinese occupied Aksai Chin. Anyway, locals on both sides of the border believe there is an underground UFO base in this region. Please enlighten us to inspire. Okay, let's see where is this Konkala place. Let's do that. Let's put the map on the screen and let's search for it. Konkala Pass. Where is it? Let's zoom in. Boom. There you are. Let's take a look at the terrain. So this is the region. Let's zoom out a little and let's see where it is. Okay, Konkala. So as you can see, it's actually within India, but it's on the line of actual control between Indian territory and Chinese occupied territory. So what's the deal with this place? So it seems that there have been reports of unexplained aerial phenomena. So what we call UFOs. Yeah, there have been some picture. Let's see what the pictures look like. Let's see Konkala. Let's see what it looks like. Konkala, and let's put that on the screen. Give me a second. Let me put that on the screen. Is there something interesting that the screen is offering us? Here we are. Aha! Certain strange images have been captured. Not sure how true this is. Obviously, the images are quite grainy. But yeah, it is said that there is there are phenomena over here that cannot be explained through conventional explanations. And maybe there are UFOs there may be a UFO base, underground UFO base. Who knows what it is? Locals on both sides of the border, I don't know about the other side of the border of the LAC. Yeah, and there have been many such reports in the Himalayan regions, even the Mount Kailash region. People have photographed, even taken videos of strange unexplainable lights near the summit of the mountain and so on. So we don't know what it is. I don't have the information. I don't have the any idea of what's really happening. I've not been there, and I'm obviously not privy to any classified or sensitive information. How can what are the possible explanations of these UFOs? One is that maybe the army, the air force is testing certain aircraft that have not been revealed to the public. You know, futuristic aircraft and spacecraft that may have those circular designs or whatever. That is a possibility. Or maybe there are actual aliens that are visiting these places for whatever reason. Or maybe it's just some defect or artifact in the camera lens or whatever that is causing such images. So we don't know. But as long as we don't capture undeniable, unambiguous evidence, we will not know, right? So, what I can tell you is that we don't know what's happening there. In the future, if more evidence emerges, we'll know. But as of now, we don't have an idea. Santosh says, I have heard that aliens have infiltrated human society, and some of the prominent world leaders are actually aliens. And they have a grand plan of turning the human species into fodder of aliens. It reminds me of a series, a science fiction series I watched as a kid. It was called V, sci-fi series V. Let me show that to you. So this is the newer remake of that. I don't know how good that was, but this is the original one. So in this science fiction series, you had these aliens who who come to Earth on these massive giant spaceships, yeah, that look like flying saucers, and they look like humans, but they are hiding the true nature because beneath their skin they are reptiles, reptilian faces and all that, and their objective is to enslave humanity and use humanity for food or something like that. Yeah, so that's the kind of story it was, and it was I kind of loved it. I think this came out in the 1980s or something. So not many people remember this series, but it was very entertaining and very exciting for me because I loved aliens and I loved science fiction. It was the perfect intersection of two genres for me. So yeah, that's the kind of hypothesis that we are seeing here, that aliens have infiltrated human society. And some of the prominent world leaders are actually aliens. Well, some leaders I can actually think of who do look like aliens somewhat. I will not name them for obvious reasons, but it's an interesting prospect. Um, do we have evidence for this? Obviously not. But yeah, there are these theories, conspiracy theories about reptilians or whatever, which is what this series was about. Yeah. So yeah, who knows? Maybe some world leaders actually do look like they kind of do remind you of aliens. Anyway, okay, with that we have come to the end of today's questions, but let's take a look at some live questions. You guys got some questions for me? Oh, I can see some interesting names coming up. Mark, who's Mark? I wonder who's Mark. uh, okay, let's take some live chat questions. I can see some names from India also turning up as candidate alien leaders. uh, okay, Saurabh says, what is a warp drive and warp speed? So this is what is a warp drive? It is the basic idea is the warping of space time. So like we have discussed many times, we live in four dimensional space time. That's what general relativity tells us. It is an extremely successful theory that explains everything we see at the large scale structure of the universe and all that. So what general relativity tells us is that we live in four dimensional space time. That's the fabric of the space time that we are immersed in. Now we know that gravity, according to general relativity, warps, bends space time. So what is a warp drive? It's a hypothetical theoretical drive in which you can use the warping of space time to create a bubble that travels within space time or something like that, and it can possibly travel faster than the speed of light. So you're not actually breaking the laws of physics. You're creating a bubble that travels within space-time. The warping of space-time, the ripples in space-time, so to say, travel faster than light, which is allowed. Yeah, that sort of thing. So that is what a warp drive is. It is what you find in science fiction novels and movies and series. Uh, warp drive was popularized by Star Trek, I believe. Yes, warp drive, warp speed, all that. So warp speed is a warp drive in operation, which achieves superluminal velocities. But yeah, well, um, obviously we don't have the technology to do that. Maybe someday in the future we could have it. But it could be allowed by the laws of general relativity. Yeah. Okay. What are other questions? Utkarsh says, how energetic particles like photons could be something but have no mass. So photons, why don't they have mass? Because they do not interact with the Higgs field. In quantum field theory, the world is made up of fields. Everything we see is just an illusion. All particles are local. um, they are local disturbances in space time, in these fields. So there is an electron field, and every electron in my body is part of that electron field, and so on. So there are 17 fields in the standard model, and there is the Higgs field. So photons are particles, are bosons that do not interact with the Higgs field. The Higgs field is what gives the universe its mass. The interaction with various particles with the Higgs field gives these particles mass. If a particle interacts strongly with the Higgs field, it has a high mass. If a particle interacts very weakly with the Higgs field, it has a low mass. And if a particle simply doesn't interact with the Higgs field, it has no mass. So photons do not interact with the Higgs field, therefore they have no mass, but they have energy. Photons are packets of energy. Yes. Now we have the most famous equation in physics, E equals mc squared, by which energy has an equivalent mass, and mass has an equivalent energy. And so that's how photons do have energy which is equivalent to mass, and that's why you can construct a black hole out of photons only. You know, you can construct a black hole mathematically using the laws of quantum mechanics, and you can create a black hole just out of photons. It's a different kind of black hole from the black hole of general relativity, but yeah, it does. You actually can do that. So yeah, that's your answer, dear sir. Let's see what else do we have. Karan says, what will happen when fossil fuels get exhausted? Well, then all of that will be released as carbon into the atmosphere. You'll have a significant amount of carbon in the atmosphere, a lot of global warming and all that. Yeah, the global warming will happen because of that. And of course, we will have no more fossil fuels, no more petrol, diesel, kerosene, jet fuel, whatever to burn, no more coal. And then we will have to look for other sources of energy. So we better get going and start experimenting with various different technologies. So yeah, that's at the rate at which we're going, we could have maybe a century more of fossil fuels, and then everything will possibly uh, get exhausted, and then we'll have to find some other ways of acquiring or extracting energy. People are asking me questions about history. I don't know why they do that on a science day. Please don't do that. We'll discuss history tomorrow, I promise. Today it is about science. Right, where are we? What do we have? What's my opinion on homeopathy? Homeopathy is the placebo effect. So homeopathic practitioners have found excellent ways of inducing the placebo effect, and that's why it seems to work in certain cases. Yeah, but it obviously can't cure cancer or any serious diseases. So that's my opinion. It's a nice way of inducing the placebo effect. What is quantum entanglement? It's when you have a system of two or more particles that has a single wave function. So you can't describe the any of the particles alone. You have to describe the system as a whole, and if you know the properties of one part of the system, you immediately know the properties instantaneously of the other part of the system. Let's say you have a particle with spin 0, which splits into two particles, with one particle with spin up, with particle with spin down, and they go in different directions. After a million years, they are, let's say, 10 light years away from each other. So the distance is 10 light years. Now let's say I measure one of the particles and I see it is spin up. Then I will immediately, instantaneously know that the other particle, which is 10 light years away, has spin down. So I know by looking at one particle instantaneously the properties of the other particle, which is 10 light years away, or maybe a million light years away. So you kind of have this information that I'm getting about a particle that is a million light years away instantaneously. So that looks like information traveling faster than the speed of light, kind of, right? But it's not quite so. But yeah, that's how it is. It's a very spooky property, and that's what quantum entanglement is, in very brief. In very, yeah. What else do we have? Pratik says, can spinning black holes radiate gravitational waves as accelerating masses do radiate? Yes. Spinning black holes will give, what they will do is they will kind of drag space-time with the spin. So the black hole is spinning, and the spinning of the black hole will cause space-time to be dragged along kind of with it. So let's say you have a ball in water and you spin it. The water kind of is dragged along with the spinning of the ball. It creates this vortex kind of shape, right? So similarly, a spinning black hole will drag space-time with it, and any kind of uh, any such thing in space-time will give off gravitational waves. So yes, spinning black holes do radiate gravitational waves. Merging black holes radiate gravitational waves, and so on. Yeah. So that's the answer. They do radiate gravitational waves. Does life exist on other galaxies? Well, we don't know. We don't know. It may be so, but we have never found any unambiguous evidence of that. Um, what is a white hole? A white hole is a certain kind of solution of the Einstein equations of general relativity, in which is the opposite of a black hole. So white holes. So we know that black holes have an event horizon. White holes also have an event horizon. For a black hole, the event horizon is a point of no return. If you're falling towards a black hole, if you cross the event horizon, you can never come back out. In the case of a white hole, the event horizon is the place beyond which you cannot go inside. A white hole is like a time reversed black hole. A white hole spews out matter and energy and radiation. It cannot absorb anything. It's like a time reversed black hole. And apart from that, a white hole could have very similar properties to a black hole. The gravitational effects would be more or less the same. So in some cases, in some galaxies, you have these active galactic nuclei which spew off enormous amounts of light and radiation and mass, these jets of radiation coming out of them. Some scientists believe they actually could be white holes spewing out radiation and matter. And we still don't know how to figure out whether it's a black hole or a white hole. So yeah, so that's what a white hole is. It is like a time reversed black hole. Um, do you believe in the multiverse? We don't know if a multiverse exists because we have no evidence of it, but it is possible it could exist. So I say 50-50. Maybe yes, maybe no. I don't know. I don't believe things. There's no belief in science. You look at the evidence and the data you have, and then you based your understanding of the universe based on that, on the evidence. Do we have evidence of a multiverse? No. So that would indicate that a multiverse, well, that doesn't prove that the multiverse doesn't exist. So that's why it's not exactly science, it's not falsifiable. So it's possible, but we don't know. Gaurav says, what do you think about the theory of brain capacity use? That what if we use only 15 or 20% of the brain? um that's not quite true. There are these popular science fiction depictions of humans only use 2% of the brain or 10% of the brain capacity. That is not very quite true. um what are the movie, Limitless or something, right? Limitless. You take a brain and suddenly you expand and you use all of your brain capacity. The brain functions in a certain way. You start fiddling with it, you're going to have problems. um, so I do not agree with the theory of brain capacity that only 5% or 10% is being used. There is something called the subconscious brain that we are not aware of, the subconscious mind that is active, but we are not aware of it, you know, and it manifests itself in a variety of ways. When we are asleep, we are dreaming. That is the subconscious mind at work. When you play sports and you have learned behaviors, that is subconscious mind coming and manifesting itself in your let's say your cricket bowling or golf swing or whatever. That's your learned something that is a result of your muscle memory and so on. So it's not quite true that we use only a little bit of the brain's capacity. We actually use all of it. Okay, where else are we? What else do we have? um Lucy, yeah, a movie called Lucy. Yeah, I think I'd seen it. What else? So this is a question I asked a few seconds ago. Can there possibly be intelligent life on other planets of the solar system before on Earth? Possible, but we don't have evidence. Possible. It's not impossible. Okay, what else? Uh, my opinion on Sheldon Cooper from Big Bang Theory. It was a fun series to watch initially. I had actually watched a few episodes of the first season. It was very funny, very hilarious. Physicists aren't quite like that. Today I think everyone believes that physicists behave like Sheldon Cooper. Not quite the case, but yeah, it was a very funny series, especially in the first season. Afterwards, I don't know what happens. And Sheldon Cooper was obviously the most interesting and the funniest character. Yeah, the stereotypical, archetypal, theoretical physicist. Do we have any other interesting questions? Shaheen says, "What's a magnetar?" I think a magnetar is a highly magnetized pulsar, if I'm not mistaken. A pulsar is a star that pulses in radio frequency. Yeah. So a few times every second, or every few seconds, it gives off this radio frequency pulses, radio waves. Uh, and initially, it was when pulsars were discovered, it was believed that it was thought that these are signals of from alien civilizations, because they were so repetitive and so, I mean, yeah, so well, exactly spaced apart in time. Yeah. But eventually it was discovered that it's a kind of astrophysical object, a pulsar. I think a magnetar is a highly magnetized pulsar, if I'm not mistaken. Haven't studied magnetars in depth, but yeah, I think that's what it is. How can we use Wikipedia intelligently? So for science, when it comes to science, Wikipedia is a good source, reasonably good source. The thing about Wikipedia is that it can be edited essentially by anybody, so you have to be careful about the information. If you want to study science, you better study science from your textbooks, or from textbooks are the best source. Yeah. But yeah, Wikipedia is good. It is good for referring to things and looking at the latest research. So I would say the most intelligent way of using Wikipedia is to look at the sources, the references that Wikipedia gives. Yeah. And you can look at the references because they could be more authoritative, but you always have to remember at the end of the day that Wikipedia is could be wrong about various things. When it comes to history, it's very often wrong. There's a lot of distortion when it comes to history, but in science it's more typically a better resource than for history. So the most intelligent way to use Wikipedia is to use it for gathering good references, but then you will have to study the references and judge for yourself whether they are reliable or not. But it's a great place to uh, gather references. Okay, let's take one more question for today. Once again, you get questions about history. uh, Harsh says, don't donate to Wikipedia. That's the best way to intelligently use Wikipedia. I agree with Harsh. Don't donate to Wikipedia. Um, Anything else? Anything else? Once again, I'm getting questions about history. I, ju- there's a reason why I stopped doing those video chats. You know, remember I used to do video chats once in a while. I would invite people to talk to me face to face on video chat. I stopped doing that. The primary reason is that people simply don't follow the rules. If today is a science session and I get somebody on video chat and they start asking me questions about history, now I feel sorry to tell them to go away and you're breaking the rules, because people simply will not follow instructions for some reason. Today is Today's live stream is about science, but I see over here in the live chat people asking me questions again and again and again about history. I just don't get it. Why do you guys do this? Stick to science for today. Tomorrow you can ask questions about history. Tomorrow. Shall I get... While I'm saying this, people ask me this. Okay, this actually is not about history. How do you retain so much knowledge? Okay, that's not a bad question. Okay. How do I retain so much knowledge? How do I retain knowledge? First of all, I read a lot. I've been reading a lot since I was a kid. Maybe since the first novel, full length novel I read it when I was 7 years old. It was a novel written in the 19th century called The Coral Island. So yeah, I've been reading for a very long time since I was a kid, and my reading speed is very, very high. I can read very fast. I can read a single page in like a matter of seconds. It's something that I have developed over a long period of time. So yeah, it's not some superpower that I have. It's like a muscle. You build a muscle over time. It takes years to build muscles, right? Similarly, the reading speed becomes better as you read more and more. So my reading speed is very high. I am very comfortable reading a lot. It's what I've been doing for years. So typically, at least for me, I I find it easier to gather knowledge by reading than by watching videos. For some people, podcasts are a great thing. Fine. Everybody is different. So for some people can gain a lot of knowledge by watching podcasts, by listening to podcasts, by watching various YouTube videos. For me, the best way to gain knowledge from my perspective is by reading. Secondly, I always give myself permission to forget what I read. I tell myself I will remember only what I find interesting. So I buy books. I Many books I don't finish them, or in some books I only read certain sections, whatever I find interesting. And the moment it stops, it stops interesting me, I give up. Try to read a little bit more, but if it stops holding my interest, I give up. I stop reading. So I give myself the permission to forget everything. That way, I remember what I find interesting, and that's how I learn. So typically, if you have a textbook and you are told to study it, you are told to memorize every goddamn thing. You have to memorize every sentence. You have to remember every equation. You have to remember every line or whatever it is. That's not how I read. That's not how I study. I give myself permission to forget as much as I can, as much as possible. My objective is to forget everything, only retain what is interesting, and that's how I always operated, and that's how I learned. So maybe it's something you guys can try if you think it makes sense to you. And with that, we are at the end of today's session. We have once again crossed 2 hours, which is the objective these days. Right? All right. So today's session is done. Thank you very much for the questions and for the wonderful chat. And I will see you in tomorrow's session, which will be a different topic: history, geopolitics, current affairs, etc. Until then, take care, and I'll see you soon. Bye.